Yes, sir.
Okay, so if you don't have any question, let me go ahead.
Sir, I have a question.
Okay, please
Sir,
go.
in the Purvi, in this method of initial rates, you said
Yes.
that we have to keep the concentration of B constant. So how are we gonna keep the concentration of B constant during the process?
Oh, I didn't say that we have to keep the concentration constant. What I told that we have
Initial
to
con-
measure the rate of reaction during initial period where very small amount of reactant has gone to product. Okay, and again the second thing what I told you is that this method is generally applicable for slow reaction. So for example, if something happens in like 4 or 5 days, some reaction completes in 4 or 5 days, so initially during 10 to 20 minutes uh, your amount of reactant which goes to product will be negligible. In that case, we can take as the concentration of reactant as initial concentration.
Okay, sir.
Is it clear?
Thank you.
Okay. Any other question? Can you see slides?
Yes, sir.
Yes, sir.
Okay. So let's go ahead. So this was the method which I discussed. Uh, this is generally used when it is difficult to measure the final concentration value or final value of physical property. For example, if you are dealing with a very slow reaction, the physical property uh, at infinite time, which means that at completion of reaction is very difficult to measure. And so we need to avoid measuring this physical property at infinite time. And for that, we developed this equation. We discussed this in the last lecture. So this was the equation. And in this, if I plot log P naught minus P, sorry, not this, this one. Okay. So yeah, ln pt minus pt plus tau versus t, then if it is a first order reaction, you will get a linear line with the slope equal to k. And this is the basis of Guggenheim method. The second method which we discussed last time is this method, KS method, which is known as KS method, and in which basically what you are trying to do is you are dividing this Pt minus P infinity by Pt plus tau minus P infinity, and that will be equal to exponential k tau. And if you solve this or simplify it, you will get Pt is equal to this whole quantity, which is a basically constant, and plus Pt plus tau exponential k tau. Okay, and in that case, we plot Pt versus Pt plus tau, and then if we are getting a linear line, then we know that we are dealing with first order reaction, and the slope will be equal to exponential k tau, and from that you can measure the value of k. So this is all about measuring, rate constant, or knowing how to, uh, get the information that a particular reaction is first order or not. Okay, so next step is, once we know that this is the rate law, can we know the mechanism? And that is one of the very important application of kinetics. And what I told you in the last lecture, that yes, main use of or main application of kinetics is to know the reaction mechanism. And for that, I started with one of the very important point, that if order is equal to a stoichiometric equation, a balanced equation, a stoichiometry in the balanced equation, then uh, then there is a chance that it involves only one step, uh, which may not be true, but in most of the cases, your reaction involves only one step. But if order is not equal to a stoichiometry of a balanced chemical reaction, then certainly reaction involves more than one elementary steps. Okay, so this is one of the very easy way to know that whether a reaction involves more than one step or not. Okay, so now I several times I discussed that what is the elementary reactions. Means what I mean by elementary reaction. That's I'm now going to discuss. Uh, so this is same thing what I have written. When the reaction order doesn't correspond to a stoichiometry of the reaction certainly involves more than one elementary reaction or one elementary step. Elementary steps are of different type, and three different elementary reaction you can think of. One is reversible elementary reaction. A going to be with reversibly, means A is going to B and B is also going to A. So this is one of the very important elementary reactions. The second is what is known as consecutive elementary reaction, A going to B and then B going to C. And then parallel reaction, A can go to B and A can also go to C. So these are the three most important elementary steps of a complex reaction. So any complex reaction will consist of a combination of these three elementary steps. Okay, these three elementary steps. So reversible elementary reactions, some of the steps may be reversible. Then conjugative elementary reactions, some of the steps will involve intermediate, and then parallel reaction, A can go to B and A can go to C. So what we will do first, we will discuss this elementary step in detail, and then we will move and see that from the rate law how we can derive the mechanism of the reaction. So first I will start with conjugative elementary reaction because this is the most important elementary step. Uh, if you go into SN1 mechanism or E1 mechanism, your intermediate is carbocation. Sometimes you have a carbon ion. Sometimes you have free radicals. So most of the reaction involves intermediates, and that's why this step is quite important. So now we are going to discuss if we have a conjugative elementary reactions, then how does rate law looks to be. Okay, so this is the conjugative reactions, A going to I and I going to P. Okay, then let's discuss about how we can write the rate law for A, rate law for I, and rate law for P. Okay, so it is quite simple to know that dA by dt will be equal to minus Ka into A, and this is very easy to very easy to solve. It will give you A is equal to A naught exponential minus KAT. This is first order reaction, and that's what we get for first order reaction. Okay, so this is quite easy to solve. Now di by dt, the way we can write di by dt is equal to Ka into A, because this steps forms intermediate is formed from A, and so we are writing Ka into A. But intermediate is also consumed in this step. So intermediate is getting consumed in this step. So we can write minus Kb into I. So this is your rate law for intermediate. Di by dt is this thing. Okay, so now question is how to solve this, and this is a differential equation. And now we are going to solve it. The way we can solve it, we know the value of a. So a is a naught exponential minus kat. So we can write like this. Okay. Now let me go and solve this for you. So please mute yourself. Okay, so what did we write is suppose A is going to I and I is going to P, and this is your K1 or Ka, you can write anything, Kb. Okay, so what we are going to write is di by dt. The way concentration of I will change with time is Ka into A minus Kb into I. We can simply write di by dt is equal to plus, let's write, bring this side. This is the way we are going to solve, is equal to K1, and then you can write A is equal to A naught exponential minus Ka into T. Am I right? We have already solved A. Now what the way we are going to solve this differential equation, that let's multiply this by exponential kbt multiply by exponential kbt. So what we will get is di by dt into exponential kbt plus kb into exponential kbt into I is equal to K1 A naught exponential Kb minus K into T. Now, why I did that? That now you can see this. And this is differential of what? Can you tell me? This is d by dt into, we can simply write d by dt into
concentration of I equal
I
exponential
exponential
kbt.
kbt. Right. Okay. And then this is equal to this quantity. So yeah, so you can simply write yeah, K1 A naught exponential Kb minus Ka into T. Okay, and then if you integrate this, take dt this side and integrate, then what you are going to get? I into exponential Kb into T is equal to what you are going to write? Ka A naught. This is indefinite integral if exponential Kb minus Ka into T plus divided by, क्या होगा divided by? Tell me.
KB minus K.
Kb minus K plus constant. What will the value of constant? Can anybody say? Tell me. At time t is equal to 0, what will be the value of I?
0.
0.
0. So this part is 0. What is the value of this? Exponential kb minus k into t? T is 0.
1.
1.
Negative of constant.
So what you will get?
K.
Minus kb minus. Is this okay?
Yes, sir.
And
Yes,
then you put it here. Okay, so let me go another. Okay, so what did I write is I into exponential kb into t. Kb into t is equal to k1 ka a naught exponential kb minus ka into t divided by kb minus ka minus, what is the constant? Ka into a naught by kb minus k. Am I right?
Yes, sir.
Yeah, so let's take common ka a naught kb minus k, kb minus k. So this will be exponential kb minus ka, okay, into t minus 1. Now what I will do, that I will take this thing, this side, right hand side. So ka a naught kb minus ka, and what I will get here if I divide by exponential kbt? Tell me.
Exponential minus k.
K into t. Is this okay? And what about here? Exponential
Minus kb into t.
kb into t. So this is your equation, I. And then we already know A, we know I, and we also know that A naught is equal to A plus I plus, क्या था product लिखा था last?
P.
P, am I right? So I can get the value of P. P is A naught minus A minus I. You already know A and I, and so we can put it here and we can get the value. Okay, you can take A naught common. A is what? A naught exponential minus Ka into T, and I is this. So A naught can be taken common. So, so now you understand how to do this, and this is the same thing. Okay, so I is equal to this value Ka into Ka minus Kb into exponential. Is this okay? Minus K into T minus Kb exponential minus Kb into T into A naught. That's what we got. Yeah. So see this one. Okay, and that's what we get. Okay. So P, you can calculate this, and P will come out to be this. This is the way which I already discussed. We know the value of A and we know the value of I, and so we can calculate the value of P. So let us go and see. So this is the value of P. Okay. If you want to note it down, just you can note it down. Uh, anyway, I am going to share this slide to you. So this is the value of product. Product is A naught 1 plus k into exponential minus kbt minus kb exponential minus kat divided by kb minus k. So this is the equation which is important to know. Okay, and you should also know how to derive this. It is not very difficult. If you know how to solve differential equation, you can do it quite easily. If you have this equation, now we are going to discuss some special cases here. One is, so this was the equation which we started with. Let's assume KB is quite greater than KA. What does that mean? That this step is fast, this is slow. So slow step followed by a fast step. So what will happen? Since KB is quite big, so exponential minus KBT will be quite less than minus KA into T. Okay, and KB minus KA will be equal to KB. Okay, because KB is quite greater than KA. So now if you look at this, what happened? This KBT, this term we can neglect, and this KB minus KA is equal to KB. And so we can simply this KB cancels out. What is left is simple equation. P is 1 minus exponential minus KAT into A naught. Okay. Now you can take the different case. Ka is quite greater than Kb. In that case, what I will get? Exponential minus K into T will be quite less than exponential minus Kb into T, and Kb minus Ka is equivalent to minus K. Am I right? Because K is quite bigger than Kb. In that case, what I will get P? P is equal to A naught into 1 minus 1 plus, let's skip here. So what is getting neglected here? Exponential, this part, K into T. So this part getting neglected. So what you are left with is Ka exponential minus Kb into T divided by minus Ka.
Minus K.
All right, Ka cancels out and minus अगर आप यहाँ पे करोगे so then you will get P is equal to A naught 1 minus exponential minus Kb into. Is this okay? So
Yes,
this
Yes,
is
sir.
when K is quite greater than B, and this is when this is a small k. So please always keep this small k because big K is always equilibrium constant, not rate constant. Okay. Now you see this. If Kb is quite greater than Ka, then P is this, while Ka is quite greater than Kb, then this is the value. One thing you will notice here, which is very important thing to keep in mind, that if Kb is quite greater than Ka, then P is dependent on K. Whereas if Ka is quite greater than Kb, then P is dependent on Kb. What does this tells you? This tells you that product amount of product depends on rate constant of slow step. Okay, in this, which is the slow step? The first one. Well, Kb is quite greater than Ka. So this is the fast step, this is the slow step. So product depends on Ka for this reaction. If K is quite greater than Kb, then what happened? Again, it is depending on rate constant of the slow step. So you must have heard about that slow step determines the rate of reaction. Slow step is the rate determining step in the kinetics. Have you heard about that?
Yes.
Yes, sir.
Yes,
Yes,
sir.
sir.
Slowest step determines the rate of the reaction. That comes from this only. Okay, so you don't need to solve. If you know that one is slow step, then you can simply write, this equation for a product. Okay, any question here?
Sir, in the derivation you used K1. What is K1?
K1, did I use K1? Okay.
So I think you replaced Ka with K1.
So just please, sometime this is the K. I did K only, am I right?
Last
So in the next line you
यहाँ पे
next
लिख दिया था. Okay. So yeah, please just that is always K and K1 always get interchange. So this should be what? This should be यहाँ तक ठीक था. यहाँ पे K होगा, am I right? And this will be K. K होगा. Is this okay?
Yes.
ठीक है. So sometime that is always a problem that sometime I replace K by K1, but when I say K1, I mean, K. Okay? Is this okay?
Yes,
I
sir.
think here it was okay. Everywhere I used K. यहाँ पर भी K ही है. यहाँ पे K. Okay? Is this
So I had
clear?
a doubt from last
Yeah,
class.
please.
Should I tell it now or at the end of this class should I ask it?
नहीं, आप बताओ अगर इसमें है तो कंजिक्यूटिव से
नहीं सर, पिछले
रिलेटेड है.
क्लास में हाँ मतलब पिछले क्लास में आपने बताया था, मतलब वो डाउट था कि जब आप फ्लडिंग मेथड कर रहे थे तो उसमें मेथड ऑफ इनिशियल रेट में
अच्छा,
हम लोग
वो लास्ट में पूछना. ओके,
हाँ ठीक है
बिकॉज अभी कंजिक्यूटिव डिस्कस या तो शुरू में पूछा होता आपने तो इट्स
सर हैंड रेस किया था बट पढ़ाना स्टार्ट कर
Oh,
दिया तो आपने
sorry,
देखा नहीं था.
please, I don't see, so whenever I ask, please just let me know. That time you can just, because it is, I'm not able to see the flags here. Okay.
ठीक है सर.
So, is this okay? In this consecutive, everything is okay or not?
Yes, sir.
Okay, if it is okay, then
Yes, sir.
let's go ahead. So, this is the thing. On that basis, what we derived, we can say that rate of formation of final product depends on only the smaller of two rate constant. Or A is I slow, then this step is the rate determining step. Okay. So please keep this thing in mind that the slowest step is the rate determining step. Okay. Now suppose, now I am going to discuss two different cases, one in which the first step is slow and the second in which the second step is slow. Okay. So let's go to this consecutive reaction. First step suppose is slow and the second step is fast. Then if I, yes, hello, tell me, any question? Okay, so first step is slow, second step is fast. Then how does this plot look like? So plot of A, reactant will decrease with time, product P will go like this, and concentration of I will look like this. Okay, so this is your concentration versus time plot. This is again very important to understand. Why this is happening? Initially this is slow, so I is getting formed very slowly, but once I forms slowly, or I forms to certain amount, it goes fast to product. So it means there is no time in which concentration of I can be very large, because this step is fast, second step is fast, and so you get like this. Okay, so initially there is increase there, then, but if you think about, you know, how this concentration of I changes with respect to P and A, this change is almost negligible. Okay, this change is almost negligible in comparison to change in P and A, reactant or product. And this forms basis of what is known as steady state approximation, that di by dt is equal to 0. di by dt is equal to 0. It is because it is not that if you look at just concentration of I, it will change, right? But what we are looking at, change in concentration of I with respect to product and reactant, it will be simply negligible. Okay, it is simply negligible. For example, here change may be like 0.005, where here change is 1,000 times more or 10,000 times more in reactant or product. So in comparison, I is almost constant, and that makes the basis of a steady state approximation. And this is very significant. This is very significant approximation. Again, approximation, it doesn't, it means that this is not exactly 0. What it means is, you know, in comparison to the change in reactant or product, the change in concentration, or simply concentration of I is constant, so change in concentration of I is almost 0. Okay. Why this is important, I am going to show you next. Okay. So I will again start this same reaction, which we, we solved it to get the concentration of I. What was that? di by dt is kb into A minus kb into I. Now you remember how did we solve it? And now if I use a steady state approximation, then this will have 0 value. di by dt is equal to 0. I is kb into Ka into kb into A. You see, in one step I got the concentration of I, and this is simply Ka by kb into A naught exponential minus K into T, because A I already know. Just in one step I know what should be the concentration of I, and that is significance of a steady state approximation. Okay, then dP by dt, Kb into I, dP by dt is Kb into I, which is equal to, Kb into I is equal to Ka into A, and we know Ka A naught exponential minus K into T. When we solve that, we will get this equation, and that equation we got it when we solved differential equation. If you remember, if first step is slow, then P will depend on the rate constant of the slow step, and you see within 1 minute we are able to get what is the amount of P. You may not realize the importance of this because this is, I've taken simplest conjugative reaction, but suppose it is not very complex. In that case, solving the differential equation will be very tough. Right? But if I take the steady state approximation, it is quite easy to know the concentration of intermediate using a steady state approximation. Is this okay? Is this clear?
Sir,
Yes, sir.
steady state here does not mean that the concentration of I will remain constant.
A steady state, if you see this, a steady state tells you that it is simply that concentration of I will remain constant with respect to A and P. There will be change, but if you look at the change in comparison to change in reactant and product, that will be negligible.
Okay, sir.
As such, it remains constant. It is changing. Certainly, if I just look at concentration of I, it will change. But if I compare the change with respect to A and P, it is going to be negligible. And that's why we can write di by dt is equal to 0. Okay? And that really solves our purpose, why we are using approximation. And you can see that I'm getting the same equation. Am I right? If you remember initial thing, then I'm getting the same equation. There I didn't make any assumption. Okay, there I didn't make any assumption, and I got same equation, which I am getting using the steady state approximation. That's what matters, right? So, but for this, first step should be slow, and the second step should be fast. More appropriately, I can say when concentration of I remains small, very small in comparison to A and P, then only I can apply it. If suppose here concentration of I is greater, then I cannot apply. There will be decrease which cannot be neglected in comparison to decrease in concentration of A or increase in concentration of P. We can't do that. So very important criteria is concentration of I should be small. Should be very small in comparison to concentration of A and P. Okay, so this will only work in that case. But suppose first step is fast and second step is slow. In that case, I will not go very fast to product. So I will accumulate and it will slowly go to product, and so concentration of I will be high. I will show you the graph of that. In that case, you cannot apply a steady state approximation. Okay, steady state approximation. Ruchika, can you say them? 10 minutes just. Okay, so a steady state approximation you can only apply when first step is slow and second step is fast. More appropriately, I can say when concentration of I is very small in comparison to reactant or product, then I can apply. But when I am able to apply, then it is very easy for me to solve the differential equation. In fact, I don't have to solve the differential equation. I just put 0 and I can get the concentration of intermediate. Okay, concentration of intermediate. Okay, luckily, most of the reactions follow this particular sequence. First step is slow and second step is fast. It is quite clear. For example, intermediates, in most cases, if you look in organic chemistry, which you have gone through, like sometime carbocation is formed, carbanion is formed, free radical is formed, and those are very unstable species. An unstable species has tendency to go to product very fast. So first step is generally slow, second step is very fast, particularly when carbocation, carbanion, and those things are involved. In that case, we can simply go ahead and apply a steady state approximation. and then I can get this equation quite easily. So almost always we apply a steady state approximation for the simpler reaction, but I will discuss more complex reaction where rate constant may be almost equal, or so in that case what we should do. In that case certainly we cannot apply a steady state approximation. Okay, any question here? No, then I will go to next step. Okay, so this is the second. K2 is quite greater than 1, K1, then KB, you can take KB. So please just keep that thing in mind. Sometime I will say K2, that I mean it is KB. So A going to I, this is fast, and I going to P slow. Then you can see that this is for A, this one is for P, and this one is I. You can see here. Okay. In that case, I cannot apply a steady state approximation. If I want to do, then I have to solve differential equation. I have to solve differential equation. Okay.
Excuse me,
Now,
sir.
yeah,
In the
please.
previous slide, the K2 is greater than K1, but in the reaction, K2 is smaller than K1.
Let me see. Here K1 is
Smaller.
K1, K1, Ka is quite a smaller than Kb. Okay, then only this will happen. Okay, then I can apply steady state approximation. Now you go to this slide. Kb is, so I did write wrong, probably, yeah. So in this case, let me write this. Ka is, yeah, sorry, quite greater than Kb. Okay? Is it clear?
Yes, sir. It is.
Okay, so please keep this thing in mind. Okay, A to I is fast and I to P is slow. Then this will happen. It is quite clear. You can think about this forms fast and this is going slow. So certainly this will accumulate, and that's what you see here. In that case, you cannot apply a steady state approximation. But some of the reactions follow this course, and in fact, sometimes intermediate is more important. Certainly that will not be carbocation, carbanion. That must be a semi-stable compound. And sometimes this is the more important product. So we should know how to, how to calculate the concentration at this. Okay. So this is the same thing which I'm discussing, and then you can know the time at which you can get maximum, and that you know how to calculate that, and then put in the I equation, you can get what is the maximum amount of I. At what time, first thing is at what time I can get the maximum I, and what will be the concentration I max, and this value is given. Okay. In the tutorial, I will give you one question related to that, and I think you can do if you understand differential, how to get the maxima. So using the differential, so that you can calculate yourself, but this is the time at which you can get the maximum amount. And that's why, sometimes here again you can see that why kinetics can be useful. Okay. Now, next question is, when are conjugative and
So,
single state? Yes, please.
so in this graph, as the time passes by, the concentration of I is always greater than concentration of A. So is that something which we did consciously,
No,
or?
no. Where, for example, at this time, A is greater, right?
Yes,
At
sir.
this,
No, I was saying
okay.
about as the time reaches infinity.
Now again, this will decrease. Yeah, this will decrease. It can go beyond This is for one reaction, but it can go beyond reactant also. So it is not true always. It depends on what is the value of K1 and K2, Ka and Kb. So it is not, but it will go like this. It will increase, and this increase will not be negligible in comparison to, or this concentration of I will not be negligible. Okay, so just you have to keep this thing in mind. This can go below the concentration of reactant. Again, it will depend on how fast this is. If it is very fast, then it will go beyond this, below the concentration of reactant. Okay? Is this okay? Any doubt?
Yes, sir. To get these two processes, like if we say that we add a catalyst which decreases the rate of the reaction, so can we say that it will lead to the first condition in which A to B is slow and I to P is fast?
It is difficult to say. Okay? This is for general reaction.
Okay.
Okay, when you add catalyst, both step can go, activation energy for both step can go down, making both processes fast. How it will going to affect first one, how it is going to second one, it is difficult to say. That activation energy of first step can go down very much in comparison to the second, or vice versa. There is also a possibility, but that we will discuss when we will discuss catalysis. Okay, here you simply you have to keep in mind that first step is slow and second step is fast. So I concentration of I is not going to negligible in comparison to reactant or product. And so I cannot apply a steady state approximation. So this is very important point which you need to keep in mind. In that case, I have to solve differential equation. We have already solved that. All right. And so, is this okay? Can I go ahead?
Yes, sir.
Okay. So now second question is, after this, can I know that reaction goes through, you know, 2 step or 1 step? Is it possible to know? So certainly there are other ways to do it, but just by looking at how product or reactant changes with time, can I know that reaction follows 1 step or 2 step process? Okay. So let's see here. If K1 is greater than K2, again K you can take, K is greater than Kb. In that case, A is going to be same in both processes, but since K1 is quite greater than K2, so it will depend on K2 because this is the rate constant for slow process. So this is this thing. Now you see this, that A, change in A depends on K1 and change in P depends on K2. So if I do just a fitting, simple fitting, exponential fitting, A versus time T, then the rate constant which we will get is different than rate constant if I just look at product with time and try to fit it. So when these two rate constants are different, then it is quite easy to say that it involves 2 steps. It involves 2 steps. So rate of formation of product is different than rate of decay of A, and it is quite easy to say in this case particularly that this reaction follows 2 steps, or that reaction involves an intermediate. So just by looking at how A changes with time and how P changes with time, we will be able to say whether intermediate is involved or not. But in this case, it is not possible through similar process, you cannot say that this reaction involves one step or two steps, because you can see here that A depends on K1 and P also depends on K1. So rate of formation of product is same as rate of decay of A, rate of decay of A. But if this is the case, then it is quite easy to tell just by looking at the kinetics, how A changes with time and how P changes with this. It is quite easy to tell. Okay. So I think I will stop here, and then there was one question, I can discuss that. But Sarthak has asked, that is about flooding. So let us go and see.
Sir, here in first part, when K1 is greater than K2, then we can say that it involves two elementary steps.
Yes.
And
Am I
in
right?
second one, we can't.
We can't say.
Okay.
Is it quite clear? Am I right?
Yes, sir.
ये जब भी different होगा, तो I know that intermediate is involved. But in this case, it will be same. And same, it can be in one step, or अगर one step भी होता तो यही हमें मिलता equation. And second, if it involves two steps, then I will get same equation. The equation is not going to be different. Am I right? And so I will not be able to say, so for example, A to P or A to I to P, both have same equation. If I deal with, I have this way, okay, K1 is quite less than K2. So this is K1 and this is K2. If that, then I will have same. Either I follow this one or this. And so it is not possible to just by looking at kinetics of means, or looking at concentration of A with time or concentration of product with time, I will not be able to say whether it follows this equation, it follows the below equation or below scheme. It is not possible, right? But in this case, it is possible. A going to P certainly will not have rate constant different, because in that case, equation will be this. And for A going to I, going to P, that we follow this thing. A to P will follow this one. In this, K1 is, you see, same rate constant. Whereas if it follows, means K1 is quite greater than K2, then this K1 and K2 will be different. Is this okay?
Yes, sir.
Okay. Next question
Before
is,
moving to that, question, can you show the difference between the 14th and 16th slide? In both, I felt like first reaction was slow and second was fast. 14th and 16th slide. A is slow here, and in 16th also A is slow, right?
नहीं, A to I fast होगा ना?
Okay, okay.
ठीक है?
Yes,
आप
sir.
ऐसे सोचो ना, A to I is fast and I to P is slow, then only I can get a higher concentration of I. Am I right?
Yes, sir.
Just ऐसे सोचो, I जल्दी बन रहा है and then it is not going to P very fast. So इसका formation जल्दी हो रहा है.
What
Decomposition
about 17th slide in that?
17th, I just discussed same thing. Did
Okay,
I?
so 17th is
Here I probably put wrong thing. Okay.
okay, okay.
Maybe that is your confusion. Okay. ठीक है.
हाँ,
ये आगे वाला पीछे वाले का ही था हम डिस्कस कर रहे हैं.
ठीक है सर.
Sorry. ये सब sometime it happens when you make the slide. Okay. So anything else?
सर वो पिछले क्लास वाला.
हाँ. So flooding में yes.
सर डाउट ये
That
था
is
कि like
rate of reaction. How to calculate rate of reaction? Am I
yes
right?
sir.
Yeah.
Yes sir.
So yes, that is a good question. In that case, certainly we cannot, we cannot measure the total property. So the question was, this is method of initial rate. method of initial rates. What I told that in that case, if D rate of reaction is simply rate of reaction is equal to K into A naught alpha, ये बता दिया था मैंने, am I right? And B naught beta. इसी का बात कर रहे थे ना तुम?
Yes, sir.
Initial rate का ही बात कर रहे थे. Now question is how to get rate of reaction. That was the question, because in this case certainly we cannot look at the you mean this
dA
thing.
by dt equal to
Yeah, so minus, this will be minus dA by dt. Stoichiometry कुछ होगा, suppose one है तो, or I have to look at minus dB dP by dt, or we have to look dB by dt. Sorry, this is plus dB by dt, something like that. Okay, so generally this is done by spectroscopy, or maybe titration. If suppose base is getting formed, then titrate with acid, so that can be done. Here you have to find out a way. Sometimes what people do, that if A plus B going to C plus D, C plus D, if I know some dye who can react with A, so with time I add dye, and then I look at look at the concentration, because only A binds with dye, and so if we look at the absorbance, suppose, so absorbance will be proportional to concentration of it. Sometimes even if suppose there is a aromatic compounds, all are aromatic compounds, then if you look at UV vis, have you seen UV vis spectra?
सर absorption spectra जो कोई या फिर normally बस electromagnetic spectrum उसका.
Yes, so so normal spectra I am talking about. So what will happen, that A may give peak here, B may give peak here.
Yes, sir.
Am I right? Something like that. If this is possible, then what you can do is look at how this absorbance changes at this position. Okay, this lambda max, this is lambda value, and this is absorbance. Okay, absorbance versus lambda. So this is how a spectra looks like. So you can measure, if you look at the absorbance with time, that will give the value of minus dA by dt. And if you look at absorbance of B at lambda max, certainly there should not be any contribution from A. In that case, you can also get dB by dt. So here spectroscopy is the most important. For example, NMR. Have you heard about NMR?
Yes, sir.
Yeah, so there are some peaks will be there in the NMR. There is a chemical shift versus for the different protons, and there will be peak like several protons. And if you know that this peak is due to product, then you can look at the how product changes with time.
So with time उसका peak जितना change होता है उसके हिसाब से
हाँ,
dA
बस वही देखना है. That will let you, that will tell you, sometime क्या होगा, इसमें से 3-4 में से एक ही में chromophore है. One reactant only has chromophore. Then only one peak you will get. Okay. अब इसमें मान लो base है, so I can do also titration. Similarly, like optical rotation, if I know that only one is optically active, then I can see that. So there are different ways in which people do this thing. For example, protein, or एक मैं simply example देता हूँ, protein ligand interaction में. Protein has a chromophore, tryptophan, ligand may not have. So यही absorb करेगा. Okay, so somebody who is working in protein field, they look at the drug protein interaction through that. Okay, protein has like you people must have you now are studying life sciences also, am I right? One course
Yes,
on that. Huh?
environmental science पे कर रहे हैं, मतलब life science पे.
फर्स्ट सेमेस्टर में कुछ नहीं है कोई ऐसा कोर्स बीटेक के
नहीं
लिए?
सर।
Okay. So, but you know that know something about protein, am I right?
हाँ सर।
Okay, and tryptophan is, for example, chromophore because that is a benzene ring that has a benzene ring. So this absorbs around 280 nanometer. Okay, so people look at that. Then there are like fluorescence, which is emission spectra. People look at that. So if particular compound has lambda max absorbance of fluorescence intensity at particular wavelength where other doesn't have any contribution, then that can be used as to determine the initial rates, means rate of the reaction. Okay.
Okay, sir. So, but you told like you can use optical rotation and also. So, but you also told that any property Y can be used to check. You gave that equation, right?
Yeah,
Finally,
any property, but that should
so
be.
that Y is, if Y is optical rotation, it's also being used to tell the rate and it's also being used to tell that equation. So both the things are being done by the same thing. So we'll have to see the whole optical rotation of the solution and also change of individual optical.
No. So just keep in that thing in mind. You cannot take whole. That's why we generally use. You see, whole solution for that region. The integrated rate law is the best because there we don't. So here, if only one has optical rotation, probably you can use it. Okay? But if everyone has optical rotation, reactant and product, and the optical rotation is a combination, rate of reaction you cannot calculate.
Yes, sir.
In few cases you can do that. Is
Exactly, नहीं कर पाएंगे, मतलब mix हो जाएगा ना उसमें.
But it is not like general case the way we discuss integrated rate law.
Okay, sir.
That cannot be done. Integrated rate, that's why mostly we generally use integrated rate law to know the order of reaction or rate constant. But if there is some problem with that method, then we come to this method of initial rates. Okay?
Okay, sir.
So there are like, suppose it is not that you cannot do that. For example, aldehyde, koi reaction hai. You know how to get the concentration of aldehyde. Right? Aldehyde का अपना well known reactions है जो निकाल के आप टेस्ट कर सकते हो कि ओके ये टेस्ट जाता है या नहीं जाता है. And somehow it can be related to quantitatively to the concentration of aldehyde, then you can know. Okay, for example, even FTIR spectra, aldehyde has its own peak that can be used to. So, you have to see which kind of reaction you are dealing with. Good thing about integrated rate law is I don't have to worry that, A, B, C, D is contributing to that signal or not. If all are contributing, still I am okay. If two of them are contributing, it is okay. But here, what we have to find out is a particular physical property which is quite distinct in comparison to the physical property of other species in the solution. Is this okay?
Yes, sir.
Okay, so one of the elementary reaction I have discussed, the other I will discuss in next class. Okay, anyone, if anyone has any other question? No? So I will stop now.
Thank you, sir.
Okay, welcome.
Thank you, sir.
Okay, see you.
Thank you, sir.